My plan was to go over today the reactions that amines undergo that you'll need to know about. And I can think of about 2, maybe 3, that we've already covered. I feel like we talked about this the last time, but I don't really remember it. And if I don't remember it, possibly nobody else does. So I might just cover that quickly again. And then there's another one that I realized, I say in the class notes, you're not going to be responsible for, since it's in chapter 10 also. Now, normally this chapter here is that we're in right now, I think is actually chapter 11. So you see it presupposes that we've already covered that material in chapter 10. So that being said, we have extra time. I think I might as well at least show you the basics of that reaction, since it's one of the few things that amines can do. It's certainly not something I'm going to emphasize on the exam. I'm certainly not going to ask 10 questions on this one idea. It'll be a lot if I ask even 2. But that being said, this reaction of amines with acid chlorides, or also called acyl chlorides, is, I think, something you can understand perfectly well. And it's a way that you can convert an amine into an amide. So I think we might as well go over all of these, and maybe then we'll do our reef session, and then I'll get us started on chapter 18, which is on nucleic acids. And we're going to get our first taste of thinking about biomolecules and biochemistry from the perspective of the field of organic chemistry. And as I think I've mentioned, in my experience, this is not me saying it, this is students bringing back word to me. In my experience, this makes for very good background for students, so that when you go on to your upper level biology or biochem classes, it's the sort of, rather what I mean is I'm going to cover here the sort of material that is exactly not what those professors will talk about. But I think having a solid, let's say, structural background in these biomolecules, so that you know what they're made of and how they're put together, can only be helpful in the context of those upper level classes. And that's something we can already understand. At least that's what I hope to convince you of. And even now, you'll notice that we're jumping around chapters quite a bit. But the order that I'm doing things in, there's a method to my madness. So here we'll have just covered amines. What are nucleic acids made of, at least partially? Well, big heterocycles that contain nitrogen. In other words, heterocyclic amines. And we'll just have talked about amines and how they behave. So I think it will be something we can understand. So one thing that we talked about in the beginning, since I have time, I even want to be super thorough with you guys and actually point you to a specific section of chapter 11. This is, this is in 11.4. We talked about how to make amines by alkylating ammonia and also alkylating other amines, that you can turn a less substituted amine into a more substituted amine. And we've defined the word substituted already. If something's more substituted than something else, that means it has fewer bonds directly to hydrogen and more bonds directly to things that aren't hydrogen, like alkyl groups. So we gave that definition already. That was in the class the last time. And we mentioned, here I'll just give an example of such a reaction. We said that you can take either ammonia, which is inorganic, or a primary or secondary amine, such as, how about propylamine? And as long as we have a large excess of this amine to make sure that we don't get a mixture of polyalkylated products, you can then treat this with pretty much any alkyl halide, preferably primary, meaning something CH2 ClBrI. So maybe let's go crazy. Oh, that looks horrible. That's better. Let's say that we took this organic iodide. And at first, what will happen is everything that's attached to the halogen will now attach to the nitrogen. And we even gave the mechanism. It's not that complicated. The lone pair on nitrogen forms a bond to the carbon that bears the halogen atom and breaks the carbon-halogen bond. And so the electrons in that bond wind up on the halogen atom, and you get a halide ion. So that's something you talked about in Gen Chem. You're familiar with Cl-, Br-, and I-. And so the first intermediate you get, it's actually a two-step process, but the first intermediate that you get still has any remaining hydrogens still on the nitrogen. The nitrogen will then have a plus charge, and then you just put whatever is here that's attached to the halogen, you just put that onto the nitrogen. Looks like I have 1, 2, 3 CH2s, 1, 2, 3, and then effectively an isopropyl group. Let's make sure I didn't gain or lose any carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes, we're good. So do you see how I just took this group and just stuck it onto the nitrogen? And the nitrogen will then, as a result of a plus charge, because it forms that bond to carbon with the electrons in the lone pair. And so for our next step, we need to treat this with some strong base. Usually this is going to be hydroxide ion, the most common metal hydroxide salts being potassium and sodium hydroxide, of course. Probably this will be done in aqueous solution. So it may say water underneath here also. You know, Owl will like to mix it up like that. But essentially, all the base is going to do, and this mechanism is not hard either. As I've said, I'm not going to emphasize mechanisms very much. They may make their way onto exams a little bit, not a ton. But this mechanism is especially simple. It's just an acid-base reaction. The hydroxide ion donates one of these electron pairs in the oxygen and picks off one of these protons. It wouldn't matter which one in this case, they're the same. And so that then allows us to break that nitrogen-hydrogen bond. In fact, the hydrogen will have 2 bonds to it, and that's no good. Hydrogen only wants 1 bond. And this arrow here is showing us putting this electron pair onto the nitrogen atom, and that gets rid of the plus charge. And so we've gone from having a primary amine, this amine is primary. You can write 1 degree like that as an abbreviation for primary. You don't have to, but you can. It's an acceptable abbreviation. And so we'll get now a nitrogen with the propyl group still, and I have this thing with 6 carbons, 1, 2, 3, 4, 5, 6, if I'm not wrong. 3, 4, 5, 6, yep. And there's still, of course, that hydrogen that's left. So effectively, we've gone from a primary amine to a secondary amine by virtue of this reaction that we discussed in 11.4. So we covered this a class or 2 ago. It's kind of all running together for me. But we already covered that reaction. And so in this way, you can convert ammonia to a primary amine. You can also convert a primary amine to a secondary amine. And you can even convert a secondary amine to a tertiary amine as long as you use a large excess of the ammonia or amine component. As long as that's the case, you're fine. So what this means in terms of what you have to know is the following. I don't want you guys just memorizing this example that we did in class. You need to understand it. What I would suggest you aim for is if you're given an amine you've never seen before, and asked to treat it with an alkyl halide you've never seen before, can you come up with the product? I'm somewhat negotiable on the mechanism. I think here the mechanism's pretty simple. I think it'd be really great if you were at least somewhat familiar with it. You know, I certainly would never go through any mechanisms of like 5-step processes with you. This is just 2 pretty simple processes. One of them is an acid-base step, which we know about acid-base reactions since Gen Chem. And this one actually we'll learn more about in chapter 6, but even already I think it's a mechanism we can understand. That being said, that's what I would aim to be able to do. And the way you'll know if you can do that primarily is I think with the OWL questions, because you'll have noticed that OWL is pretty good at coming up with molecules you've never seen before. So that's what you should aim for, not memorizing what we did in class, but being able to apply the information in a different context, or really the same context, but with different particulars. And the best way to do that, the way that you get to the point that you know what you need to know, is by practicing. There's just no shortcut. But I certainly OWL questions can help. If you come across other questions in your adventures on the internet, or you find some good stuff in YouTube videos and you work on some of that and you want to bring it to office hours and ask me if you're doing it right, please don't hesitate. That's what I'm here for. Good, so that's one kind of reaction that amines can undergo. We also allegedly talked about amines reacting with strong acids. I think I vaguely remember it, but just to give an example, let's say that we had benzylamine. So recall that pH is a benzene ring, pH is C6H5. And if you don't like using pH, you don't have to. You can just, in fact, you can write C6H5. Or if you just want to write the benzene ring out, you could do that too. Let me show you another perfectly correct way to draw that molecule. So here's our benzene ring. And we're going to have, we're going to have CH2NH2. And it does not matter on which of those 6 carbons you put CH2NH2. It's the same molecule. Not only would I not take off points, I wouldn't even notice. It would register to me as the same compound, which means you guys need to practice until you can easily see that all of those are the same and it doesn't trip you up. Make sense? But I feel like putting it here today for no special reason. And of course, you can put the lone pair of nitrogen either above or below. It's the same thing. So if you don't like using pH for phenyl group, you can draw the molecule like this, perfectly fine. You can even, maybe instead of writing pH, you like C6H5, absolutely fine, perfectly acceptable. Because C6H5 is unambiguous. There's really only one way to put together 6 carbons and 5 hydrogens, and this is it. So if you wanted to write benzylamine like this, it's perfectly fine. I have absolutely no objection. You pick whichever way works the best for your learning style. And even though our exams are multiple choice, so I won't be grading you directly on your structure drawing, it's of course going to be to your great advantage to be able to draw structures properly. But the details of how you do it, that will differ from person to person. That's basically about personal taste. But you use whichever works the best for you. I have no preference. Well, maybe I do. I tend to be a pH guy, but I don't know. I certainly am not trying to turn you all into clones of me. That would be weird. Anyway, we can treat this amine or any other amine with a strong acid, such as, well, here's a different one. How about perchloric acid? That's one you learned in Gen Chem was a strong acid, HClO4. Well, the rules are the same. The proton in the acid is going to wind up on the nitrogen, and you will go from a nitrogen with a lone pair that has a charge of 0 to a nitrogen with a plus charge, and no lone pair and one more proton on it. So you would get the conjugate acid of benzylamine, the benzylammonium ion. And I don't think I really care if you know that it's called that, but it does have a name. So that extra proton came from the perchloric acid, and so the conjugate base, the perchlorate ion, is still going to be around, ClO4-. Do you see how we took the H from the acid and put it on the base? Does that make sense? And isn't that exactly what you learned in Gen Chem, that acids and bases do? Acids give up H+, and bases accept H+, at least if we're talking about Bronsted-Lowry acids, which mostly is what we mean when we talk about acids and bases. I personally would look very askance at that species. Organic perchlorate salts are stupidly explosive, so I don't really know why I picked perchloric acid, I guess just to make a point. And there are researchers who have to work with these things, and it's extremely dangerous. I'm thankful I've never had the pleasure of working with organic perchlorates, but they're very, very, very dangerous. Why do acids give up hydrogens to base? The reason that acids give up protons to a base is because by giving up the proton, you get a more stable species. And that's going to be always the case. That's part of the definition of what an acid is. And bases just are species that are able to accept that proton and still give a reasonably stable species. But all acids have that in common. The reason they give up H plus is because their conjugate bases, which is what you get after it gives up H plus, are more stable. And the more stable that conjugate base is, the happier the acid is to give up the proton. In this case, if you were to look at the structure of the perchlorate ion, I don't really want to go too far off base, but you would find this is one of those hypervalent things. I think we're going to find the chlorine is something like 14 electrons around it. Let's see. ClO4, wait a minute. ClO4 minus. Oh, I know. Yep. This is one way of drawing it. The perchlorate ion. Did I say it right? 4, 8, 12, 14. Yep, there's 14 electrons around chlorine, and that's allowed because chlorine's at least the third level of the periodic table. Those elements can become hypervalent like this and have more than 8 electrons around them. They don't have to, but they can. But I think you'll immediately see this species is resonance stabilized. I can think of at least 3 other resonance forms, because I could just as easily have made this oxygen the one with the single bond and the minus charge, or this one, or this one. So what you get once you lose the proton, the HClO4 just is the H on the O, it's just OH. But once you lose that proton, this anion that you get is very well stabilized by resonance. And so that's why it's such a strong acid. If you used H2SO4, would both hydrogens attach to the amine? No, and there's 2 ways that you can know that, and I'll show you both of them. Let's just even change this to H2SO4. One way that you can know that is by looking at what you get after H2SO4 loses a proton. You get the conjugate base, the bisulfate ion, HSO4 minus. And the proton here is acidic. It can be lost, but it's significantly less acidic than sulfuric acid. And the way you know that is you were told in Gen Chem H2SO4 is a strong acid. You were not told that HSO4 minus is a strong acid. It is still an acid, but it's a pretty weak acid. So that's how you know there's a significant difference. And you could look up the pKa's of the first proton that comes off and the second one. I certainly don't ask you guys to memorize things like that. But if you looked it up, you would find that the difference in pKa is pretty dramatic. I mean, sulfuric acid probably is a pKa like -3 or -2 or something like this, something stupidly low. I bet if you looked up the bisulfate ion, it might be 3 or 4, something like that. I would bet in any case it's easily 1,000,000 times less acidic, or 1,000,000th as acidic as that first proton is. So that's how you know not to take the second proton. The other way you know not to take the second proton is there's no place to put another proton. Nitrogen already has 8 electrons around it, and that's the maximum. There's no way you can put another proton on it. You'd have more than 8 electrons around nitrogen. So I would say in both those 2 ways, you can know that you don't put both protons on. So you don't just have to memorize it. It kind of makes sense. Is that kind of what you meant? I just want to make sure I answered the question. Good. Why a plus sign and not a double bond? Same reason. Because if you made a double bond, then nitrogen would have 10 electrons around it. The reason it has a plus sign is because it used the lone pair, much like it did up here, to pick off H plus from the acid. And we could draw the mechanism of that as well, although I wasn't hoping to go through it quite this much, but it's not that complicated. Although that looks like a sideways parenthesis. Come on, Jack. There, that's better. But what will always, without exception, happen is the lone pair on nitrogen is going to reach out and grab something. So sulfuric acid would have a structure like this. Again, the sulfur atom is going to be hypervalent. I think the sulfur atom in sulfuric acid has 12 electrons around it. We'll find out in a second. So let's see, 4, 6, 10, 12. Yep. So the way this works is the lone pair picks off the proton. Again, remember, it's very tempting to show an arrow from the H. This H goes here. That's not how we use arrow pushing. Remember that arrows are only and always used to show movement of electron pairs, never of atoms, never of charges. They should always start where the electron pair starts and end where the electron pair ends. This arrow here shows that it's going to form a bond between the nitrogen and the hydrogen, and the electrons in that bond, remember a bond is 2 electrons, the electrons in that bond are going to come from the lone pair in the nitrogen atom. At that point, we will also break one of these, or break this hydrogen-oxygen bond, and this arrow here means that we're taking the electrons in that bond and putting them onto the oxygen. So that oxygen will now have a minus charge. That's not bad. Oxygen is a very electronegative element. It's very good at stabilizing a minus charge. Not only that, but once you did that, you'd find another very well stabilized species by resonance. When you put the minus charge in this oxygen, if you work it out, you'll see you can just as easily put the minus charge on this oxygen or on this oxygen. So again, you get a species with a minus charge that's very happy, very stable, because it's stabilized by resonance. No wonder this proton is so eager to fall off. The second one's a little harder to get off because the species already is a minus charge. And you would then go to the sulfate ion, which is a charge of -2. Here it only is a charge of -1, so that makes a big difference. Anyway, once you do that, these are the species that you get. You get the conjugate acid of this amine, and you get the bisulfate ion. So, like I said, I'm not going to emphasize mechanisms like this very much. That doesn't mean you don't have to know them, but it's not something I'm going to emphasize very heavily. There may be occasional questions on that sort of thing on the exam, but certainly not like 20 questions. But be that as it may, I think it really helps us to understand what's going on better. So, right, I think that's all I really have to say about amines reacting with strong acids. You get the conjugate acid of the amine. Remember the definition of conjugate acid, you had this in Gen Chem, is what you get when you add one H and a plus charge. So that's what we mean by the conjugate acid of something. When you add one H and a plus charge, if you've effectively added H plus, then you have its conjugate acid. Likewise, the conjugate base of something would have one fewer H, and the charge would then go down by 1 rather than up by 1. That's why the bisulfate ion is HSO4 minus. We took away an H and we took away a plus charge. Do I add an addition sign for the end product? You mean like here? You can, you don't have to. Makes no difference. Either way is fine. You'll see it both ways, in fact. Good. Other questions then on that reaction? Well, let me clear some space here. And again, this last reaction, I really spent the entire time just absolutely certain that I was going to be talking about this today. And then I looked more closely and it says, we're going to learn this reaction later. And that's true. I certainly would emphasize this only barely on the exam. Maybe 1 or 2 questions at most. But I don't think it hurts for you guys to be exposed to this reaction now. It never hurts to see things twice. But we're certainly going to cover reactions like this in chapter 10, which is on carboxylic acids and derivatives of carboxylic acids. So first of all, I should mention acid chlorides are also called acyl chlorides, ACYL. In fact, we've defined the acyl group already a couple classes ago. And the definition of an acid chloride or an acyl chloride, call it whatever you like, is as follows. I'm going to give you the definition in a structure rather than in words. But it's related to carboxylic acids, related to aldehydes and ketones, related to all of those other compounds like it. So I would say the definition of an acid chloride is a carbonyl attached to a chlorine on one side and some alkyl group on the other. One would think that in theory, it could be possible for R to be a hydrogen. That structure we would still consider an acid chloride. However, as far as I can tell, that compound where R is a hydrogen does not exist. It would be the acid chloride of formic acid. And I've never heard of it. I've never seen it available anywhere. I conclude that it's just too unstable. So the smallest acid chloride you're likely to run into is where R is a methyl group, CH3. That's acetyl chloride. And actually, you might have used that stuff if in any chemistry lab, maybe even in high school, you made aspirin from salicylic acid. Actually, I don't know if you used acetyl chloride. You might have used acetic anhydride, which is about 10% less nasty. Well, okay, really more like about 30% less nasty. They're both nasty, but with acetic anhydride, at least you're not breathing in HCl all the time. You know, you're only breathing in acetic acid, so it's a little bit less bad. Good, and the only reason I'm mentioning that amines can react with acid chlorides is it's a reaction we can already understand. The mechanism's a little complicated, so here I certainly won't do the mechanism. But even without a mechanism, it's not that hard to figure out. So let's take, oh, I don't know, let's go crazy. Let's take this cyclic amine, which again happens to be called pyrrolidine. I don't think I really care if you know that, but it does have a name. And let's say that we treated this with acetyl chloride. So methyl group, chlorine over here. All you need to know is it's the exact same type of idea as with alkyl halides. Remember how we said you look at what's attached to the halogen and you stick that on the nitrogen? Same thing here. You look at what's attached to the chlorine. And I will say, by the way, I think in general you'll find this is always chlorine. Acid bromides do exist, but they're much less stable and there are far fewer of them available. Acid chlorides are common as the proverbial field mice. So I think in practice you'll find this will always be chlorine. This one could be chlorine, iodine, or bromine with alkyl halides. But this, I think you'll find it's going to be pretty much always chlorine. But the idea is the same. You just take whatever is attached to the chlorine and stick it onto the nitrogen. You'll of course wind up with a plus charge because that hydrogen is still there. Right, I think you'll agree with me that I've just pulled off the halogen and just stuck everything onto that nitrogen. It'll wind up with a plus charge. And after this, you do need to neutralize, kind of like you did over here. I will say, if it were me, I would not bomb it with hydroxide. I would want to be very careful because actually the compounds like this can react with hydroxide unless you're very, very careful. So there's going to be some kind of base mentioned here. It might not say KOH or NaOH. It might be a weaker base. Honestly, between you and me, if I were going to do the neutralization step here, I would use something like baking soda, sodium bicarbonate. That's a much milder base, and I wouldn't have to worry about it reacting with this molecule. This would simply pull off the proton. You've probably seen the baking soda and vinegar reaction. Vinegar contains acetic acid, which is not a terribly strong acid, but strong enough. And you see bubbles coming off. Those bubbles are of carbon dioxide, because when this pulls off a proton, you go from HCO3 minus to H2CO3. That's called carbonic acid. That's also what's in your carbonated beverages. So those are also giving off CO2 gas. And so H2CO3 is unstable. It breaks up into CO2 and water pretty much spontaneously. So that's where the bubbles come from. You would see the same thing here. And in the end, it will pull the proton off and you'll wind up with the amide. And so the way you get the structure, the way you get the answer is you just pull that proton off and It's not going to be terribly pretty, perhaps, but we'll get it in there. You just pull the proton off, and you go back to a neutral nitrogen atom. So it's a way of converting amines into amides, this reaction with acid and acyl chlorides. So, like I said, I'm not going to make a real big, huge deal about this on the exam. I might mention it once or at most twice. But I think you can agree it's not that complicated. If you can understand this reaction, you just go through the exact same type of steps with this one. And again, in OWL, it might mention other bases besides sodium bicarbonate. In real life, I would be wary of using sodium or potassium hydroxide. Those bases are too strong, and I'd be afraid of hydrolyzing the amide and going back to the starting materials. But which we'll learn more about that in chapter 10 also. But basically, you can expect here to be given some base. And if it were me, I would not use the strongest base in the world. One of our rules in organic synthesis, is at least the way I've heard it put, and I kind of like it, is you always want to use the smallest hammer you can get away with. Don't get out the big old sledge if one of those little tiny tack hammers will do the job. And this here is a tack hammer. Where did the chlorine go? You're going to get sodium chloride in the end. So that's going to wind up in some inorganic side product. Same as over here. You'll wind up with some iodide salt, in this case, potassium iodide. You'll know what you have to put based on how the question's phrased. Especially watch OWL very carefully, because sometimes they want you to put down everything. And they'll even want you to put like a separate sketcher box just for K plus and another one for Cl minus. You just need to be careful with them. So the way you'll know what you need to put is by how the question's phrased. But the major organic product is going to be the main thing. The hydrogen will not be connected to the Cl, and here's how you know that. The way you know that is because HCl is a very strong acid, and you have base around. So the hydrogen is going to wind up over here. You're going to go from HCO3 minus to H2CO3. That's where the H goes. Over here, the H is going to add to the OH. You can even see it here to give you HOH, otherwise known as water. So that will be one of your inorganic side product as well. So the way you know where the H goes depends on what you're given, depends on what the base is. Like I said, we often just leave it out. We're kind of sloppy. But if OWL does ask you to account for the other inorganic side products, the way you know what you get is by looking at the base you're given. That's going to give you an idea of what to add the H to, what to add H plus to. And you talked about reactions like that in Gen Chem. And generally, there's going to be a metal ion also, usually an alkali metal ion, K plus or Na plus. That will wind up effectively with your halide ion in both cases. So up here, you would also generate a mole equivalent of potassium iodide. Here, you would get sodium chloride. Good. So, but in terms of understanding the organic product, it's no more difficult than understanding this reaction. Good. So yes, absolutely. Please do review your strong acids. Maybe learn what are a couple of weak acids too. That would not be the end of the world. I would like, for example, you guys to know that acetic acid is an acid, but not a strong acid. That's a pretty weak acid. There are ones that are weaker still, but that would be a good thing to review. And if you want to bring some things to office hours, don't hesitate. Good. I think I've said more than enough about that. But so like I said, we'll cover this reaction again when we get to chapter 10. But I see nothing wrong with mentioning it now. I think you guys can handle at least hearing about it. And I think you'll agree, if you look at it with an open mind, it's not any harder to understand than the reaction of amines with alkyl halides to give other amines. The only difference is here, because of the carbonyl, you actually wind up with an amide. So if you've forgotten about amide functional groups, AMIDE, please review that in chapter 1 when we went over functional groups. Good. That's all I can think of to talk about amines. Any other questions on any of that? I mean, that's a lie, of course. I could come up with 50 more examples, but we do have to go on. Basically, my plan is just to start chapter 18 on nucleotides, just to get used to some of these structures. We'll get into the heavy-duty structure drawing. Where did the Cl go? With the Na, you get NaCl as a side product. You'll know whether or not you have to write that based on how the question's phrased. But we're mainly interested in the major organic product. So the overall reaction, if you want all the other parts, it would be this thing plus H2O plus CO2 plus NaCl. you will also get all of those other inorganic side products. And you'll know if you need to put them based on how the question's phrased. OWL especially loves doing that. And they'll want you to put this in one sketcher box and that in another, so you'll have to read the directions. But I can tell you we organic chemists are mainly focused on the major organic product. Good, other questions then? All right, well, let me see. Should we do our clicker thing? Yeah, we should. Let's take a little break. We'll clear all these. And like I said, it's just attendance today, so please be sure you've registered your attendance. Nothing will show up on REEF. You don't have to answer any questions on REEF. This is just practice. And new and improved. Oh, wait a minute. I have to do a new share of PowerPoint. There we go. New and improved. I got some feedback that some people were concerned that I don't think everyone, but some of you might have been able to see the answers. So I've heard your concerns and I'm responding. What I've done is I will just not put the answers in any longer. Not that it really matters here since it's just for attendance. But in ones where we're actually doing polling, I'll have to put the answers in later. So that way no one is to be concerned about anyone being unfairly advantaged by being able to see the answers. Okay, so, well, good. This is pretty much what we just were talking about. So I would hope that at least these first two would not be a problem for you guys now. And you can practice on this later on if you like. This is an acid chloride. If you're writing C double bondo in a linear fashion like this, you kind of have no choice but to put the O in parentheses like that. So if you ever see C and then O in parentheses, it means C double bondo. We just kind of have no choice but to draw it like that. But be sure you register your attendance. That will be automatically 10 points. I'll give you a few minutes to work on that, and then maybe we'll go over it. Will the answers be put in when you upload them to Ecampus? Yes, I will always put the answers in so that you can use these to study with and to review. But I'll leave them out until then. Or I'll put it to you this way. If I at some point forget to put the answers in, let me know. That's all. It's not a big deal. This is what I like to call a solvable problem, if that does happen. Is there going to be an OWL assignment for chapter 18 next Friday since we have the exam? Let me see. I'm not sure there's going to be anything. I think I've actually already put it up. It might all be not for grading. There just aren't very many questions there. Yeah, but double check. I think I've put up actually everything through chapter 18. And it would be, yes, we'll finish chapter 18 by then. Let me see now. See, a lot of these biochem chapters, they're going to be largely not graded. And I think the same might even be true for chapter 15 on lipids. So the answer might be yes, that it's due, but maybe none of it's graded. So you'll know, if it says not graded, it means not graded. If it doesn't say not graded, it means graded. But as I recall, they're both not graded. I think they only gave me like 4 questions total, so I don't like grading it in that case. All right. The time of the clock would be getting on 3:35. So hopefully you figured out at least the first 2. Let's go back to our, so I just want to, butylamine with HBr, then benzyl bromide, then benzyl chloride. Okay. So let's get back to our whiteboard. So we've got butylamine. There's our butylamine. And the first reaction was with HBr, as I recall. And remember what you do. The proton goes on the nitrogen, and you get the conjugate acid of the amine. So this goes in this case to NH3. Just whatever is on the nitrogen, you add one H to whatever is on the nitrogen, and you get a plus charge in the nitrogen. And yes, the bromide ion's still there also. Br minus is like the counter ion. So you'll know if you have to put that or not based on how the question's phrased. Make sense? This is a reaction of an amine with a strong acid. Then we had what? I think benzyl bromide, PHCH2Br. So remember the rules for this. The first step is you look at what is attached to the halogen, in this case benzene ring CH2. The next step is you put that onto the nitrogen, making sure that now the nitrogen is a plus charge, and that's going to be the first intermediate. So NH2 plus, and then I just put CH2 benzene ring on it, because that's what I see is attached to my halide. And yes, Br minus is also there. After this, you're going to treat this with some base, probably sodium hydroxide or potassium hydroxide. You'll be given, or should be given, what it reacts with, and that's going to deprotonate this species, and you'll go back to a neutral amine. It just removes H+, and I literally mean it's H+, it removes an H and removes the plus charge also. So you'll go back to a neutral amine. Or a term that gets used here and sounds rather ominous, you can say it goes to the amine-free base. That's a completely proper use of that term. That's a perfectly valid way to describe that. So I would expect you'd get something like that. And then what was the third thing? Benzoyl chloride. Well, again, whatever is on the halogen, we just stick that on the nitrogen. We still have these two protons. Plus, you don't have to draw it exactly like that. There's many other correct ways to draw it. So I would expect you'd get that at first, and then that needs to be neutralized. If it were me, I'd use sodium bicarbonate. I'll just write neutralize here. Owl might just say neutralize, or they might give you a particular base. And that will remove the proton. Wait a minute, one more carbon. There we go. 3, 4, yep. And you'll get this amide. So those are the answers, and I'll make sure this winds up on YouTube so you can look at the answers there also. Good. Make sense? And again, I don't expect you all to know all of this right now. There's still time, and you have to practice. But that should at least give you an idea of the landscape. That gives me 5 or even 6 minutes to start to touch on nucleic acids, and I think that's all I will need. I want to save all the real hocus pocus stuff for Friday. Well, not exactly hocus pocus. Good. Clear all drawings. So like I said, this will be on YouTube. You can look up the answers there. And besides, I'll also put the answers on when I upload the questions. So you'll always have maximum stuff to study with, to practice with. Good. Yes, today was just attendance. I'm going to kind of cheat at the moment and just go straight to my chapter 18 class notes. So everything you see here is already in your class notes. But like I said, what we're going to do now that we know a little something about amines is move to our first biochem chapter. And I kind of like spreading out the biochem chapters like this instead of leaving them all for the end, because the format's so different. And it makes the exam completely an entirely different format. And I think it's somewhat less shocking to do it this way. Good. So, but now that we know something about amines, we can look at these structures that are involved in nucleic acids, both DNA and RNA, and make some sense out of them. Yes, those molecules are kind of big, but we understand the functional groups in all of these. We see some amine type nitrogens over here. There's also an occasional amide functional group like you see over here. And I think that's about it. I think you've basically got heterocyclic amines and amides. You will also notice especially the parent heterocycles, this looks very much like benzene. And in fact, it happens to be called pyrimidine. It is very much like benzene. It's aromatic like benzene. All you've done is you've replaced carbons, CHs in benzene with nitrogens. But I think you can also see here that there's essentially two flavors of heterocycles. And we've defined heterocycle before. We defined that in chapter 1. So if you've forgotten the definition, please go and review that. But it basically means a cyclic compound with something other than carbon and hydrogen in it. That's a quick definition. But there's basically these two flavors. The nitrogen bases that we call the pyrimidines, and this is, again, the sort of thing that I promise you your biochem professor and biology professor won't mention. But these things are called pyrimidines for a reason, these three compounds. They're based on an actually existing compound called pyrimidine. That's an actual real thing. And so that's why we call these pyrimidines, because they're related in structure to pyrimidine. Likewise, we call these two species purines, because they're related to an actually existing compound called purine. Now, I certainly don't care if you memorize all these structures. I don't have them memorized myself. I think I proved that a few lectures ago when I tried to draw one of these things and was kind of choking. But some things that I think would be good for you to know, I think it would be good for you to know that the smaller heterocycles are called pyrimidines and the bigger ones are called purines. I have a kind of stupid mnemonic device for it. I'll tell you what I use. You may absolutely feel free to reject it and come up with your own. I promise I will not be offended. But the way I remember which is pyrimidine is a bigger word, but it goes with the smaller heterocycle. Purine is a smaller word, but goes with the bigger heterocycle. So the name size and the heterocycle size do not go together. The bigger name goes with the smaller heterocycles, the smaller name goes with the bigger heterocycles. It's dumb as anything, but I managed to remember it based on that. And like I said, if you come up with a better way, oh, please go for it. I promise not to be offended. But these are what you will find in the so-called, well, these are what you will find in both DNA and RNA. And where we're going to go from here is actually being able to put together small oligopeptides, not peptides, sorry, oligonucleotides. We're going to learn next time how you go from a nitrogen base to a nucleoside, and how we go from a nucleoside to a nucleotide. And that again is I think you'll find that very useful background in your biology and biochem classes, because they probably are not going to get as specific about the structures of these things as we will hear. Other than that, as I've already said, I think you are most certainly not going to be responsible for any of the molecular biology that's in chapter 18. I think I've been pretty specific about which sections you're not going to be responsible for. And so that's why you have hardly any questions that we can even ask. There might not even be OWL assignments for chapter 18. I'll double check that, of course. But if there are any, they'll be due, a week from this Friday. But what does it mean if it's due if they're not graded? And I strongly suspect they're not graded, but I'll double check. I think I have that all set up, but I'll double check that later today. Other than that, we'll learn how these are all put together to make nucleic acids on Friday. So we'll see you then.